to work on it.
Is it ball control?
Yeah.
They have like ball switches and stuff like that.
Yeah, but you can't control, like, the audio box is locked. IT doesn't want people messing with it because that's how things do get too low or too high. So I'm sure, like, I'm positive it's at the right setting in the box. I just have to figure out what the right setting is out here. So we heard you, but you might need to shout a little bit in Williston for today. So yeah, I post notes. You'll see like the lecture notes that I handed out. We're gonna work them through together. I'm gonna have them on my tablet, and then at the end of class, I'm gonna save them to PDF, and I'm gonna put them up on Canvas, so there's like a record of what we've covered. Also, the video takes a little bit longer. I have to render the video, and then I have to put it up on YouTube, and then they have to say okay, like, and then once that's ready, I'll have a link. So usually that's done by the next day. I use Canvas announcements to communicate with the class. It's good to just check Canvas periodically. Although if you download the app, does anybody have the app? Everybody have the app? It'll just alert you. It'll be like, there's an announcement from this class. So I recommend doing that. So this is how your work is evaluated. This is just a general grading rubric that I use for every math course I teach. I evaluate your work holistically, and basically just figure out, whether it's A-level work or B-level work or C-level work, right, on down the line. And I use these 3 criteria, these areas, see if it's well executed, well communicated, essentially correct, and then this sort of a description of how I assign those. I don't, if something's an A-level work, it just gets 100%. I don't really make a distinction between mid-A and high-A level work. So I just I evaluate things kind of roughly on this scale, and it is possible to get a 0 if you leave something blank, or if it just kind of totally misses the mark, like that's possible. And then every time you get something back, it'll have a little grade sheet attached to it. So there'll be a little box for each problem number, and then this number next to it is the weight. I pretty much just stick to weights of 1 or 2, so times 2 problems are just maybe more involved or harder, more difficult. So, like for example, maybe I've graded something and those problems got scored in this way. So I'm going to say a couple of things. One, what I've done here is I've circled like the number score and then indicated how each problem was on communication. The communication isn't a separate part. It's all rolled into that numerical score, but the communication is the thing that people often have a harder time gauging where their work stood on that criteria, so that's why I include it in the grading box. So then I take each numerical score and I multiply it by the weight. So this would be a 5, 4, 2, 8, 4. Then I add these up and I get the total grade points. So that's 10, 18, 23. Okay, so 23. Then I go over here to the table and I convert that to a percentage. So at 23, that's 78.43%. So the mechanism of how the grading sheet works is fairly simple. I'm going to explain to you how I come up with this table. I'm not asking you, I'm not showing you because I want you to explain it back to me. I just want to be transparent about how I come up with your grades. So you'll notice, if something is a 5, it's 100%. So if you got a 5 on every problem, you should get 100%. If you got a 5 on every problem here, it would add up to 35 grade points, and that's why 35 grade points is at 100%. If you got a 4 on every problem, you would get an 87%. We would think you should have an 87. So if you got a 4 on every problem on this grade sheet, that would add up to 28 grade points. And that's why 28 here is at 87%. And then in between these, it's linear. I just go down by the same amount. So if you got a 3 on each problem, that would add up to 21 points, and so on. So that's how I create that table. I'm going to pause here for a moment and see if there are questions. Okay. Why don't we go around the room here in Randolph first? I'm going to see who all is here.
Jacob Pratt.
Jacob.
Pratt, and I just know Jake Oaks in here too.
Okay, hold on. Jacob Pratt. And then Jacob Oaks. Jacob Oaks, okay. All right.
Caleb White.
Caleb White.
Zach Tomberg.
Zach Tomberg. Right. Zach Tomberg. And I know you, Eric.
Benjamin Fontaine.
Benjamin Fontaine.
Sarah Clark.
Sarah Clark.
Ethan Shiloh Draper.
Ethan Shiloh Draper.
James Gilbane.
James Gilbane.
Cody Cook.
Cody Cook. Cody Cook. You're not on my roster as of when I printed it out like last week, so maybe it was a recent addition.
It says
Yeah, but I mean, I'm just saying maybe it got added recently, so I'll check my roster again. But Cody Cook, C-O-O-K?
Koch.
Oh, Cook. Cook. It's pronounced Cook?
Yeah.
Okay, all right. Then you are on. Okay, good. Never mind then. And? Oh, right. I already got you. Perfect. Okay. In Randolph, in Williston, do you feel like you can shout? Yeah, okay. With the microphone on? No.
Oh, it's a bunch of people.
You want us to shout our names?
Yeah, like get really excited about it.
Shout. All at once. Is there another
Well,
microphone?
I'm Peter.
Yeah, okay, great. Hi, Peter.
Devin Dion.
Great.
Ben.
Great, yes.
John.
Was that John?
Yep.
Okay. All right, who else?
Brandon.
Brandon, great.
Jarrett.
Jarrett, perfect. Anyone else?
That's it.
Okay. All right. Thanks, everybody. So I'm Rachel. Most of you probably know me. Some of you here in Randolph may have, are only just meeting me today. You can call me Rachel. Okay. So our plan for today, so we've done this. We went over the syllabus and talked about academic integrity. We're gonna spend a little time getting a start on this course. This course is basically like a differential equations course, which is kind of like a natural next step after you do some calculus, is to look at differential equations, and then with a focus, finding some good. There are lots of applications of differential equations, but it'll be kind of like a differential equations course, and then look at some applications of those. And we're going to start with some basics. As far as background in this course, I think Calc 2 is a prerequisite. A lot of the calculus we need is mostly like Calc 1 stuff, like remembering our derivatives and some basic integration techniques. So if you're kind of solid on that, you'll be in pretty good shape. If you need to brush up on that, please do so, or we'll have an opportunity to kind of remember these things as we go. We're going to take a bunch of derivatives today as we kind of look at some of these differential equations that we're looking at. So we're just going to start with some basic terms. So usually what we want to do in differential equations, what we often do in any applied math, whether it involves differential equations or not, is try to find some relationship between its quantity, the quantity over time. That's like a pretty common type of application. When it differential equations show up in scenarios where it's easier to find a relationship between the quantity and how fast it's changing. Like, for example, one of the most basic types of differential equation applications where we see them pop up is in populations and how they grow, and it's it can be hard to model the population growth directly, but what we can do is say, you know, maybe make a reasonable basic assumption that the rate at which the population grows is proportional to how big the population is. Like the bigger the population, the faster it's going to grow. And so that would give us an equation that looks like this, you know, where R is some constant of proportionality. So the time rate of change of the population, dp dt, or p prime, is some constant times however much is there at that given time. That's a differential equation. A differential equation is an equation that involves a function and one or more of its derivatives. When we solve a differential equation, we're looking for the function. The solution to a differential equation isn't x equals 5. It's, you know, y equals f of x or x equals f of t, you know, something modeled over time. I know the function that satisfies this. So if I take that function and its derivatives, plug it back into the equation, it's true. So the order of a differential equation is the highest order derivative that appears in the equation. So this first one that we looked at, the dp dt equals r times p of t, that's a first order differential equation. It just involves the first derivative. The spring mass equation is one application that we'll look at. Mx double prime plus bx prime plus kx equals f of t. This is, even if we don't know much about the spring mass equation, I'm just looking at that, and I can say that's definitely second order, x double prime. That's the highest order derivative that appears. Same with the next one, an RLC circuit. Even if I know little to nothing about circuits, I know that this is a second order differential equation. The solution will be some function I of t, such that if I plug in I of t and its second derivative into this equation, it will make the equation true. All of the differential equations that we're going to look at in this course are ordinary differential equations. That means that they involve just the regular straight-up derivatives that we know and love from Calc 1 and Calc 2. If you take a multivariable calculus course, like Calc 3, you usually get into it, you'll see what are called partial derivatives. So I'm going to do something, I like to do little mini examples in the margins of the notes here, but let's say I have some function like f of x comma y. So f is two independent variables, x and y, and this is like 4x squared plus 2xy plus 3y squared. What a partial derivative is when you say this is the important variable, and any variable that's not that one important variable, I'm going to treat it like it's a constant. So if I found partial f, partial x, and instead of just a regular d, we use like the script d delta, so it looks like this, like partial f, partial x. That means that x is important, and I'm going to treat y like it's a constant. So 4x squared, its derivative. X is the important variable. There's 8x, right? Regular old power rule. For the middle term, y is a constant. So it's like 2y times x. I have a constant times x. That derivative is just the constant. So this would be 2y. 3y squared, if y is a constant, 3y squared is a constant, and its derivative is 0. So this is the partial derivative of f with respect to x. That's different than if I take a total derivative, like the regular derivative, like an implicit derivative, when we had to like see 2xy as like a product, and then multiply by dy dx when we need to. So this is what a partial derivative is. That's not going to be super important in this course. I'm just letting you know that those are the types of derivatives that are involved in a partial differential equation. Ordinary differential equation just means the regular derivatives that we already know. So when we solve, we're looking for a function. And the function that we're looking for is like the dependent variable that is a function of some single independent variable. That's why it's an ordinary differential equation. Sometimes it'll be like y of x, like y is a function of x. A lot of the time, especially because we're looking at applications, it'll be like x of t, because a lot of the applications, the independent variable is time. In addition to having an independent variable and a dependent variable, there are often parameters. Parameters are these unknown quantities, but they're like constant for a particular like instance. Like up here in the spring mass equation, the x is the dependent variable, and t is the independent variable. Like the solution to this would be some function like x of t. But like m, b, and k, those are all constants that just probably depend on the spring, maybe how hard it is to put like the spring constant, or maybe the weight that's hanging on it. They're all constants that depend on some particular situation, but once you've chosen your spring and you've chosen your mass or whatever, they're done, right? They're determined and they're constant for the rest of the problem. Those are what we call parameters, and it's like a different thing that's not quite a variable, but they can change for different scenarios. So an analytic solution is exactly what I said before. When we're solving a solution, it's just some function that we're looking for. So we're going to do some examples. We're going to start with a simple one. We're going to show that the function y equals e to the negative 2x is a solution to the differential equation y prime plus 2y equals 0. So if y is equal to e to the negative 2x, the first thing, I'm just going to find y prime. What's the derivative of e to the negative 2x? What's that? Guesses?
Negative 2x times
It's
L.
negative 2 e to negative 2x.
Great. So Wilson got the credit because Wilson remembered to turn their microphone on. Okay, right? So we had people like mumbling, what they thought, working out the answer, and then their microphone lights are all red. So just remember to turn on your mic. So yeah, negative 2 e to the negative 2x, because e to the stuff is our favorite function, right? It's the function that is its own derivative, and then the chain rule says you got to multiply by the derivative of the stuff up there. So there's a little side work. Now let's work out what is y prime plus 2y. Well, y prime is negative 2 e to the negative 2x plus 2 times y is e to the negative 2x. And that does, in fact, give us 0, which is what we were supposed to get in that equation. Are we having fun yet?
Yeah.
Yes. Fun fact, right now we're kind of getting used to what a differential equation is. We're going to do a lot of, taking derivatives and showing that things are solutions. We're going to spend quite a bit of time learning how to start with the different types of differential equations and then figure out what that solution should be, rather than just verifying that something they give us is a solution. As it happens, the y prime plus 2y equals 0, like that equation, it can be shown that every solution to that equation has this form, c times e to the negative 2x, where c is just some constant, any constant that's non-zero. Or actually, I suppose even if it were 0, that's a constant solution to this, because if you plugged it in, that would still work. Okay, so now we're going to look at this second order differential equation, y double prime minus y equals 0. And we're going to just determine whether each of these functions is a solution. So we need to get the second derivative. What's the derivative of sine x? Cosine x. Y double prime. What's the derivative of cosine? Negative sine.
Again, no microphone.
Well, she doesn't have one in front of her, so she's at a disadvantage. She's got a handicap that she's overcoming. So, all right. So so negative sine. Now let's plug this in. So y double prime minus y. What does that look like? That'll be negative sine x minus sine x. We have a little microphone kerfuffle here, but everything. You're gonna want to turn it around so it's facing you. Yeah, good. Feel free to just leave the microphones on too, right? That's fine, because then you don't have to raise, But but here's the thing: if you leave the microphones on, it's almost like we're just all in the same room together and we can hear each other when we say something, right? That's not necessarily a bad thing. All right, what do we get here? Say that louder. Turn on your microphone. You have a microphone now. Oh, the one in the front. There you go.
Negative 2 sin x?
Yeah, negative 2 sine x. And you know what's true about negative 2 sine x?
It's not 0.
It's not 0. Yeah. Yep. So that means that y equals sine x is not a solution. All right, let's try it again. Y is equal to e to the 2x. What's y prime?
2e to the 2x.
Mm-hmm. And what's y double prime?
4.
Mm-hmm. All right, so y double prime minus y. What does that get us?
2e to the 2x.
Oh, after you, so let's see. So we have 4e to the 2x minus y would be minus e to the 2x. Yeah, 3e to the 2x. What's true about that?
It's not equal to 0.
Not 0. Not only is it not identically equal to 0, not only is it not always 0, which is what it means to say this function is 0, but in fact this is never 0. There's not even a single value of x that makes this true, let alone being true for all values of x. So again, this function is not a solution. Should we try another? Sure. Okay. What do we get for y prime?
Negative 4e to the negative x.
Negative 4e to the negative x. And the second derivative?
4e to the negative x.
4e to the negative x, right? Because that sign just toggles the sign, right? The negative x up there.
Yeah, this one works. So this one works, yeah.
Oh, yeah. So y double prime minus y 4e to the negative x minus 4e to the negative x. That is identically equal to 0 for all x. So this is 4e to the negative x is a solution. What was, I just want to, what was it that made the function in part B not work? I mean, there's similar types of functions. They're both exponential. What messed it up for part B?
It's the constant in the exponent.
Uh-huh. So that we had a constant of 2 versus a constant of negative 1. Yep. Does it matter that there was a 4 out in front?
No.
So if I change that constant, would it still work? Yeah, because all of that, all it did is just flip the sign back and forth, right? So for this last one here,
It's going to work no matter what, because it's going to stay the same every time.
yeah. So y prime is c e to the x, and y double prime is c e to the x. So when we find y double prime minus y, we're just subtracting this function from itself. And so this function y equals c e to the x, that's a solution for any constant c, right? All we need to know is that c was a constant, and we can verify that it's a solution. Before we go any further, I just want to talk a little bit more about this example. When we look at the equation y double prime minus y equals 0, right? I could rearrange that. Often this is how they're written, in that we'll have all the terms, on one side, and it'll be set equal to 0. In fact, sometimes that makes it kind of simpler to solve. But when we solve this type of equation sort of by inspection, we say which is to say we're not going to try to integrate right now. We're not going to try to but just kind of think about, oh, what kind of function should fit this? If I rewrite this and I just throw the function on the other side, we're really just looking for a function that's equal to its own second derivative. So a function that's equal to its own derivative is certainly going to be equal to its own second derivative, right? And that's what we see happening in part D. In part C, this function is not equal to its own derivative, but because the exponent was just a negative 1x, it just toggled that sign back and forth. So all the odd derivatives will be equal to each other, and all the even derivatives will be equal to each other. The other thing I'll point out is these are both solutions. So think about what a general solution would look like. Certainly we've seen that anything that looks like y equals c e to the x will be a solution. And I think we've convinced ourselves, we just sort of talked a little bit about how in part C, the constant 4 didn't matter. Like, so if that was just an arbitrary constant in front, that should work. It was just that exponent that's really important. What mattered was the exponent was either an x or a negative x, like a 1x or negative 1x. And when you have these two solutions, these two different types of solutions for this differential equation, it maybe won't be surprising that the equation or the function, say c1 e to the negative x plus some other constant c2 e to the positive x, like that will actually be a solution, right? If these two types of functions are solutions by themselves and they make it work, then just when you add them together, notice I'm not multiplying or dividing, but I'm really just adding them together, it'll still work. And that has a lot to do with the linearity of differentiation, that when you take the derivative, you just do it term-wise. Okay, let's do one more now. We're going to verify that that this function, this given function, is a solution to the ODE. ODE is just a abbreviation for ordinary differential equation. So here, a and b, little a and little b, those are parameters. So we're going to treat them like constants. This is a second order differential equation. So let's find the first derivative. When you think you got it, go ahead and just offer up your solution for the first derivative.
Negative pi a sine pi x plus pi b cosine pi x.
Yeah. Good. Right, so we picked up a factor of pi in front of each of those because of the chain rule. It tells us to multiply by the derivative of the stuff inside, and the derivative cosine is negative sine, derivative sine is cosine. What happens when we take now the second derivative?
Just flips again with the signs.
Okay.
Signs also plus 0.
So, which signs flip?
They both become negative.
They're both going to be negative, yeah, because the first one is going to retain its negative sign.
Yeah.
Yep. What else happens?
The pi becomes squared on the outside.
Yeah, so we'll have minus pi squared a cosine pi x minus pi squared b sine pi x. Good. So now let's see what happens when we plug this in. So y double prime plus pi squared y. We're going to see if this is in fact equal to 0. Y double prime, I'm just going to substitute this in. And then plus pi squared times y. So that's pi squared times the given function. I'm going to distribute that pi squared. And then I think these cancel. So here's the minus pi squared a cosine pi x plus pi squared a cosine pi x. And the same, the minus pi squared b sine pi x plus pi squared b sine pi x. This does, in fact, equal 0. And so the given function is a solution. How's that? Pretty nice.
Yep.
Good. Okay. We'll spend a little bit of time on this next section. We might not finish it, and that's okay. Before we start that, though, I just wanted to go back to Canvas for a second. Under the modules, let me go ahead and publish this. Okay. So you're going to see, I have usually a link for each class day. So here's our link for Monday, for today. If you click on it, it lists the stuff that we're going over. So like exactly what I've got listed like here for what we're doing, and then what the practice exercises are. Usually, I give PDFs for the pages that contain the practice exercises for the first couple weeks, just in case we're having a hard time getting our hands on a copy of the book. I know Amazon has it. The bookstore
Sold out on
is
Amazon bookstore and Barnes and Noble.
all everywhere,
Yeah.
even
I
electronically.
bought the last copy on Amazon. It's not supposed to arrive for at least another week.
Oh wow. Okay. Well, I will get on the. The bookstore says it's back ordered. I'll contact them and see what's going on. But I'll have those available until the bookstore gets them in. After the bookstore has them, like I can't keep like this is I consider this to be fair use because we literally can't get our hands on a copy of the text. And then once the bookstore has them in, I'll probably stop doing it so that the publisher doesn't get too angry. I did choose a book that was a fraction of the price of the old book that used to be used. So, the old book is a good book. Like Krychek is a nice text, but in this course you would use maybe 10% of that book, and it costs like $300 or something. There's a lot of good information in it, but it's just we don't need it for all that we're doing. So I just picked a smaller book that was maybe not quite as fancy, but does the job, and I think is a quality book, and is only like $75, maybe $80. What's that?
Yeah, it did.
Oh, weird.
Right, it still works.
Yeah, it does. Huh. Interesting. Okay. All right, so let's spend a little bit of time getting started on this next section. Again, we might not finish it, and that's fine. So I mentioned that a solution to a differential equation is a function. We're looking for a function that we can plug in, but we've also noticed that sometimes more than one function will work. So when we're looking for, usually what we want to do is find the general solution, which is really the family of functions. Like anything that's going to be a solution will look like this, right? Like that's what a general solution is. If they give us extra information, like maybe I know some specific value of the function, we usually call this an initial value. Initial value, whether they give it to us for when x is 0 or when x is 1 or when x is 5, it doesn't matter, but we call that an initial value. Anything that allows us to maybe solve for that particular constant that might be involved, or that parameter. Then we can find the particular solution for that given initial value. So we'll start with an example. They gave us the equation y prime is equal to y minus x, and then they told us, they gave us a general solution. We want to verify that this is a solution, so just like what we were doing the last time, and then find the particular solution with that added information they gave us. So this is a first order differential equation. I'm just going to find the first derivative. What is the first derivative? Like the first derivative of this function here that they gave us.
Of the one with the C constant, correct?
The one what?
With the C?
Yeah. And the one in the front. It is, yeah. It's not, yeah. See, now it's on, yeah. C e to the x plus 1. Do you guys have questions? Right, so we're just taking that derivative, and now, so there's y prime. Let's go ahead and find y minus x. So y minus x, which is the right side. Y is the function they gave us, c e to the x plus 1, and then minus x. You know, simple algebra, right? Plus x minus x, those cancel. That gives us c e to the x plus 1. And this is, in fact, equal to y prime. So that's a solution. What we want to do now is this is a solution regardless of what that value of c is. We're going to try to find that value of c. We're able to because they gave us this extra information. We know that y of 0 is equal to 3, right? So that means that we can plug in y equals 3, x equals 0 into the equation. So 3 equals c times e to the 0 plus 0 plus 1. What is e to the 0? 1, right? So 3 is equal to c plus 1, and that means that 2 is equal to c. And that means that gives us our particular solution, 2 e to the x plus x plus 1. How are we doing? We've done a lot of derivatives today, a bunch of derivatives today, and now we're going to do a little bit of integration. Nothing too heavy duty, but enough to kind of just get our feet wet. Surprisingly, a lot of what you do in differential equations, even though you're looking for a function whose derivatives satisfy some, equation, solving them usually doesn't involve a whole lot of integration. Like usually we don't solve by integration. There would be different integration or different solution techniques that we're going to learn. A lot of them are really algebraic in nature. But we're going to do a couple of differential equations. We're going to solve a couple that we can do just by integrating. And these would be the types of equations we might have solved in Calc 1 or Calc 2, as we're kind of getting used to what integration is. The integration is like the inverse operation to differentiation. So if I wanted to solve this equation, so y prime of x is equal to e to the negative 3x, the first thing I'm going to do is just rewrite it. That y prime notation, I'm going to write that as dy dx, because this will be kind of helpful. And then that dy dx, I'm going to treat it like a fraction. And that's sort of abusing the notation a bit, but it is a legit move. So I'm going to multiply both sides by dx here. So that when I do that, the equation that results is dy is equal to e to the negative 3x dx. Now when we have an equation, we could do the same thing to both sides. We could multiply by 2 on both sides. We could take ln on both sides. We could differentiate both sides. We can integrate both sides, and that's what we're going to do here. So here we're integrating dy, or integrating 1 with respect to y. What is the result when we integrate dy? Y, yeah, good. And then what's the integral of e to the minus 3x dx? Nope.
Negative 1/3 e to the negative 3x.
Yeah, negative 1/3 e to the negative 3x. What are we missing here? Plus c. It is absolutely crucial when you're solving differential equations to add the constant as soon as you integrate. You only have to do it on one side. I mean, the reason we only have to do that on one side is, let's say I added it to both sides, so I had y plus c1 equals negative 1/3 e to the negative 3x plus c2. All I would do is say, oh, I'm going to subtract that from both sides, and then when their powers to combine is just some other arbitrary constant. So we only have to do it on one side, but you have to do it as soon as you integrate. This gives us the negative 1/3 e to the negative 3x because it's like a simple u substitution, right? If u is negative 3x, and then making sure we have our du would require us to have a factor of 3 in there. So this is a general solution. We're going to find the particular solution by using the initial condition. So y of 0 is equal to 1. Means that 1 is equal to negative 1/3 e to the negative 3 times 0 plus c. E to the 0 is still 1. So we have negative 1/3 plus c, 4/3. Okay, so now we have our particular solution, which is the function y equals negative 1/3 e to the negative 3x plus 4/3. What we did here gives us a sneak peek into there's going to be a lot of different approaches to, different techniques we're going to learn to solving differential equations, but the ones that do involve actual integration like this, what we did here kind of gives us a peek into one type of differential equation. So we kind of focus on what happened here. You'll notice we had dy dx, and then we wrote that as treated it like it was a fraction, and we put the dx on one side. And what was really important, and what helped make that work, was that the x's were grouped with the dx, right? The dx is over on a side with the x's. There were no y's on the right side after we did this here, right? And then here we had just y by itself, just dy, or maybe, and in some cases I might have a whole expression with y there as well that goes with the dy. But what we did there was basically separate the variables. We want the x's with the dx, we want the y's with the dy, and we don't want to mix them up. That's what kind of makes us able to just then integrate both sides. I think we have time for one more. This is over at 3:40?
Yes.
Okay. I think we have time for one more. This one is a second order differential equation. And you'll notice they've given us two pieces of information. We know the value of the function at 1 and the value of the first derivative at 1. We have a second derivative. I'm going to rewrite that in a similar fashion to the way I rewrote it before, but maybe not exactly what you think I'm going to do. So everybody here believes me. We already know that the y double prime is just the derivative of y prime, right? Okay. So I'm going to write that side as dy prime dx. So the first thing I'm going to do is just find y prime. I'm going to think of y prime as just some function I want, and I know its derivative. Almost as though I'm reducing it to like a first order differential equation whose solution is y prime. And then I'm going to rewrite the other side to make it power rule friendly. So this is 3x to the minus 2. And like we did before, multiply both sides by dx. So now we have dy prime equals 3x to the minus 2 dx, and we can integrate both sides. What do we get when we integrate the left side?
Y prime.
Y prime, yeah. And how about on the right side?
Negative 6x to the negative 3.
That's the derivative.
Negative 6x to the negative 1. It'll just be negative 6x. 1 over 6x.
No. It is to the negative 1. You have that right. But when we increase the power by 1, right? So there's our negative 1 power. And then we divide by the new power. So what are we going to get?
Negative 1.
Just negative 3.
Negative 3 x to the minus 1 plus a constant. I need that constant right off. Now, here's the thing. I also know that I'm going to have to integrate again in this process to get y, because this is going to help me find the first derivative. So I'm going to subscript my constants, because it's really bad form to use the same constant twice for two different possible values in the same problem. So we want to get in good habits here. So now I'm going to rewrite this. Y prime, oh wait, yes, we can go ahead and rewrite this. Let's go ahead and do that first. So y prime is dy dx. This guy, it looks like it's written in power rule friendly form, but it's not. Can anybody tell me why? Maybe that's a trick question.
Because it's to the negative.
What makes that not power rule friendly?
I'm not sure.
Okay. You're right, but like, what makes that not power rule friendly?
That's the integral of natural law.
Yeah, it's not a power rule integral. So, power rule friendly is kind of meaningless if it's not an actual power rule. So I'll just write it as minus 3 over x plus c1. Now, I'm not gonna do the whole integration thing yet, because we have enough information to figure out what c1 is. They told us this value right here. So I'm gonna find what c1 is first, plug it in, and then go through and solve for the other one. Sometimes we can't do that. Sometimes we have to carry constants through and then end up with a system of equations to find those. But if it's possible to get constants early on, let's do it. So y prime of 1 equals 5 means that 5 is equal to negative 3 over 1 plus c1. And c1 is 8. Cool. So dy dx is negative 3 over x plus 8. Now we'll separate the variables. So dy is equal to negative 3 over x plus 8 dx. And we can integrate both sides now. What do we get on the left? Y. What about on the right?
Negative 3 ln x plus 8x plus 3.
Plus 8x, yeah, plus a constant. Good. It is law and absolute value. That's going to become important to remember with the law rule for integration. Okay. So there's the general solution. Let's solve for that constant. They told us that y of 1 is equal to 6. What's ln of 1? 0. So what is, we get -2 for C2? So there's our particular solution, -3 ln absolute x plus 8x minus 2. Nice. Okay. Well, we will. We're just about out of time. We're going to continue with this on Wednesday. On Wednesday, I'm going to be in Williston. So, folks up there, some of you probably taken telepresence classes. Maybe some of you haven't. I'm just going to make sure that we know how to get started, get the Zoom conference started, and then you guys here will be okay to get yourself connected on Wednesday. Okay. Okay. If you have problems, you can text me. My number is on the syllabus. And also there's like a telepresence support number you could call too, like somebody could just kind of come down from IT down the hall. So. All right, thanks everyone.